This lecture is on reaction mechanisms. First, an introduction on molecularity. Each elementary step can be classified by its molecularity, which describes the number of reactant particles in the step. A forming product is unimolecular. A plus B forming products is bimolecular. A plus B plus C forming products is termolecular. Let's do a practice problem. Write the rate laws of each of these elementary steps. Determine the molecularity of each step. A plus C forms products. B, 2A plus B forms products. C, B forms products. D, A plus 2B forms products. The answers are as follows with the rate law and molecularity shown. A is rate equals K times concentration of A times concentration of C. Molecularity is bimolecular. B is rate equals K times concentration of A squared times concentration of B. Molecularity is termolecular. C is rate equals K times concentration of B. Molecularity is unimolecular. D is rate equals K times concentration of A times concentration of B squared. Molecularity is termolecular. Now, let's discuss working on determining the rate law in a mechanism. When it comes to proposing the mechanism in support of the experimental rate law, there are two key requirements that must be met. One, the elementary steps in the mechanism must sum to the overall reaction. Two, the rate law predicted by the mechanism must be consistent with the experimentally observed rate law, otherwise it is invalid. Note, the way to solve the theoretical rate law depends on the conditions of each elementary step or reaction. If the first step is the slow step, then one can determine the rate law just from the first elementary reaction. For example, consider the overall reaction between nitrogen dioxide and carbon monoxide gases. Gaseous nitrogen dioxide combines with gaseous carbon monoxide, producing gaseous nitrogen monoxide and gaseous carbon dioxide. It is determined that the experimental rate law for this reaction is rate equals K times concentration of NO2 squared. The question is, what mechanism can be proposed in supporting this rate law? Let's take a look. A possible mechanism for this reaction is a two-step process. The first elementary step is two gaseous nitrogen dioxide molecules react to form gaseous nitrogen trioxide and gaseous nitrogen monoxide, and it is the slow step in this mechanism. Second elementary step is gaseous nitrogen trioxide reacting with gaseous carbon monoxide, forming gaseous nitrogen dioxide and gaseous carbon dioxide, and is the fast step in this mechanism. Show that this mechanism supports the experimental rate law. Step 1 is to show that the mechanism equals the overall reaction, which it does. Step 2 is to determine the theoretical rate law of the mechanism. This is based on locating the slow step or rate determinant step. In this case, since the first step of this mechanism is the rate determinant step, it is determined that the theoretical rate law is rate equals K times concentration of NO2 squared. The only way to verify that this mechanism is valid is by performing kinetic studies. But since the experimental rate law is identical to what was determined, the mechanism is valid. This figure shows the energy profile for a two-step process where the first step is the slow step or rate determinant step, And the second step is the fast step, as evidenced by the high amount of energy from reactants to its transition state in step 1, and low amount of energy from intermediate to its transition state in step 2. This figure provides a real-life experience in looking at rate determined steps by observing cars passing at a toll plaza from point 1, 2, and 3. Here, at point 1 to 2 for toll plaza A, traffic is slow here, indicating that from point 1 to point 2 is the rate determined step. In the second step, while toll plaza A is fast, toll plaza B from point 2 to point 3 is slow, and thus step 2 is the rate determined step. However, what if the rate determined step is not step 1 of the mechanism? What happens here? If the first step is the fast step, then the mechanism will encounter at least one step which there is at least one or more intermediates. The intermediate will be expressed in terms of the reactant. When the first or additional steps is fast, intermediate products are built up, which will be reactants in the follow-up step, and at equilibrium, concentration of the reactants and products are related because the forward and reverse reaction rates are equal. The final rate law will be expressed in terms of just reactants. Let's look at an example. Consider the following system. The first step of this mechanism is two NO gaseous molecules in equilibrium forms gaseous N2O2, which is a fast initial step. The second step is gaseous H2 reacting with gaseous N2O2, forming gaseous H2O and gaseous N2O, which is the rate determining or slow step. The third step is gaseous H2 reacting with gaseous N2O, forming gaseous H2O and gaseous N2, which is a fast step in this mechanism. The overall reaction is two gaseous H2 molecules plus two gaseous nitrogen monoxide molecules, producing two gaseous water molecules and gaseous molecular nitrogen. It was determined that the experimental rate law is rate equals K times concentration of H2 times concentration of NO. Justified that the rate law is supported by the mechanism. Step 1, show that the mechanism equals the overall reaction. In this case, the overall reaction is supported in that two gaseous H2 molecules combines with two nitrogen monoxide molecules, producing two gaseous water molecules and gaseous molecular nitrogen by combining all three elementary steps. Step 2. Since the first step is the fast reversal process, it can be expressed as rate forward equals rate reverse. We look at the first step, which is a fast reversal process, where it equals K1 times concentration of NO squared equals K minus 1 times concentration of N2O2. It equals, in solving for the intermediate N2O2, K1 over K minus 1 times concentration of NO squared. We know and write the rate law of the rate determined step and substitute intermediates in the rate law. Rearranging the intermediate N2O2, the final rate law is rate equals K observed times H2 concentration times concentration of NO squared Here are a couple of review problems for you to work on. Question 1. The following mechanism has been suggested for the reaction between nitrogen monoxide and oxygen. In the first step, which is fast, two gaseous nitrogen monoxide molecules form gaseous dinitrogen dioxide. In the second step, which is slow, gaseous dinitrogen dioxide reacts with gaseous molecular oxygen to form two gaseous nitrogen dioxide molecules. Provide the overall reaction of this mechanism and determine the expected rate law of this system. Question 2. Nitric oxide and nitrogen dioxide are found in photochemical smoke. Nitrogen dioxide is formed from nitrogen monoxide in the exhaust of automobile engines. A possible mechanism for this reaction is given below, where equilibrium is quickly established in steps 1 and 2. What is the rate law predicted by this mechanism? The overall reaction is two gaseous NO molecules plus gaseous molecular O2 forms two gaseous NO2 molecules. The first step, which is fast in equilibrium, is 2 moles of gaseous NO forms 1 mole of gaseous N2O2. The second step, which is fast in equilibrium, is 1 mole of gaseous N2O2 forming gaseous atomic N plus gaseous nitrogen dioxide. The third step, which is slow, is gaseous atomic N plus 1 mole of gaseous O2 forming gaseous NO2. For the rest of this presentation are solutions to these two questions. Please only view them after you have tried working it on your own to gain a maximum understanding of this concept.